Is it getting recorded? Okay, fine. So module 5 is all about time varying fields and Maxwell's equations. This is first half. Uniplanar waves and wave propagation is in the second half of your fifth module. So we shall deal with the first half of your first module. Once we complete this first half of your first module, we shall start with the second half, like Poynting's theorem and some simple concepts will be covered in the second half. So I'll be trying to complete the full concepts here in the first half of your module 5. In this, we'll be discussing about Faraday's Lenz law, or also called as Faraday's law, Lenz. So this is Faraday's Lenz law, and we shall understand the concept called displacement current. Displacement current. So the name itself will tell, like current is displaced in another form, and we shall have Maxwell's equations. So in total we have 4 equations. So we shall study Maxwell's 4 equations, both in point and integral form. If you say point form, it is a differential form, and integral form, that's an integral form. So here it will be in terms of dou by dou t, and here it will be in terms of some integral with some limits. So we shall study both, and then finally we shall discuss about retarded potential. Retarded potential. And here, don't refer to the given notes. Please refer to the notes, or please refer to the content which will be given in online class. So in the printed form of notes, it's too lengthy. So I've just reduced the explanation for retarded potential in simple words, and 2 to 4 equations. So this is sufficient for us to explain retarded potential for maximum up to 6 marks. So this you'll be getting to prove displacement current. So this would be for some 10 marks, and this would be for some 5 marks, and Maxwell's 4 equation, this would be from 8 to 10 marks. So it may be a combination of 2 or 3 questions for 20 marks. So you could just now try to get a things like, okay, this might be the combination, or this and this might be the combination, or this and this and this might be the combination. So it can be the combination of any of these questions from time varying fields and Maxwell's equation. This is first half of fifth module. Am I clear? I hope you guys are clear with this syllabus.
Yes, sir.
Okay, fine. So now we shall go in detail, like what is Faraday's Lenz law. We shall take up the issues one by one. Before I start Faraday's Lenz law, You might get a question state and prove or define or explain with necessary equations Faraday's Lenz's law. So far, whatever things that we have dealt in our electromagnetic waves was electrostatic concepts, electrostatics, where the charges were at the rest and the electric field was constant, right? So it was not varying, it was constant due to electrostatics. And likewise, later we again started with magnetostatics. Here, the magnetic field was constant due to the current carrying conductor was a DC current. It was a static current. The current was constant and you obtained magnetic field which was constant. So here the fields which were electric field and magnetic field both were constant. But as the name gives, now the magnetic field or electric field are varying. See, if E and H varies with respect to the time, then we will call it as time varying fields. Time varying fields. So if assume that a magnetic field is varying with respect to time. See here, if you have a magnetic field here, like if it is varying with respect to time. So this is a magnetic field. So if this is a ground here, if this is a ground level, and if the magnetic field is varying somewhere here like this, so it's varying with respect to time. And now you have a current coil, so not current coil, or if you have a conductor or in terms of a coil, right, in the shape of a closed path. Okay, so if I have a closed path, something like this, I've just kept this terminal open just in order to measure something. This is a varying magnetic field H. H is varying with respect to time. Now, if I get this, if I get this closed path into this magnetic field, varying magnetic field, I repeat, if I get this into this varying magnetic field, okay, so what happens? What happens? This is varying magnetic field. The EMF will be induced, right? The EMF will be induced inside this coil. So there will be an induced EMF. If you measure an induced EMF, will measure some voltage or electromotive force due to this varying magnetic field. And this is related, or this can be explained using your Lenz's law. And what is that induced EMF around a closed path? Hope you got the definition here. Want me to repeat?
Yes, sir.
You want me to repeat?
Yes, sir.
Okay. I'll take the fresh page. Suppose you have a closed path. It is just a closed path. There's nothing, no current, nothing here. And if you have magnetic field varying here, if you have a changing magnetic field here, this red arrows I'm indicating the magnetic field is varying. Okay, so this red arrows are varying HB or varying magnetic fields. So if this is varying, and if you have a closed path like something like this, so there will be an induced EMF. There will be an induced EMF on the surface of this path, closed path, and that induced EMF here. So there will be an induced, there will be a, say, a movement of current due to this flux. Due to this varying flux, there will be an induced EMF, flow of currents inside this closed path. And that induced EMF around closed path, EMF around closed path will be equal to the negative of rate of change of magnetic flux. Will be equal to the negative rate of change of magnetic flux enclosed by that path. So this is called as Lenz's law or Faraday's Lenz's law. Is it okay?
Yes, sir.
And measured in some volts. So why do we have that negative sign? Negative sign indicates that EMF is in such a direction which opposes the original flux. See, minus is nothing but it is opposing the direction of the original flux. See here, you have flux, magnetic flux or flux density here. See, you have magnetic flux here at this point. See, this intersects. See, this flux lines or the magnetic varying lines intersects here. That means it is perpendicular. It is perpendicular. And these flux lines will intersect in such a way that this rate of change of flux, see here, varying magnetic field means what? It is varying with respect to time, d phi by dt. This is in such a way that this path is, and it reduces or it cuts the flux in such a way that it will generate a EMF here on the loop. Again, if you have a empty coil, see you have a coil, okay, you have a coil, this is not carrying any conductor, be careful. And now if I have a permanent magnet here, if I have a permanent magnet, I'm just trying to make you people confirm about this concept. See, I have what? Permanent magnet, and this obviously will have a flux lines, something like this, and this direction which goes from north to south. Now if I try to move this field inside and out of this conductor, okay, so if I try to move this, so this flux lines will try to disturb the charges or the particles on this conductor, on the surface of this conductor, and there will be an induced EMF. See, there will be an induced EMF when you try to vary this magnetic field inside this coil or inside this closed path. Here this magnetic field is varying. You're trying to move this magnetic field here. This kind of EMF is called as transformer EMF, where B is varying. B is varying. Is it okay? So this is almost same. This is almost same here. Like whatever you see here, this is varying B here. B is varying. And this closed loop, this closed path is static. Here also you could see this is fixed or this is static. This is not moving. Path is static. What is varying? Field is varying. Which field is varying? Magnetic field is varying. And what has happened? EMF is induced. Transformer EMF is induced into the coil where path was static. Now what I will do, I'll take the same magnet. Okay, the same magnet I have considered here, north and south, and I'll make this as static now. See, this magnet or the magnetic field is static. Okay, now this is kept static. I have this coil, and now I will try to move this coil. I'll try to move this path or a closed path. I will vary this now. I'll vary this closed path inside and out of this magnetic field. So here in this case, again the EMF will be induced on the surface of this coil. So I'll induce an EMF. So here EMF will be induced, and this EMF I'll call it as generator EMF. Generator EMF. Due to what? Due to varying path. Due to varying path or varying coil, moving coil with static field. I call it as generator EMF. Is that okay? Is this okay?
Yes, sir.
Yes, sir.
What is transformer EMF? I repeat, transformer EMF is the EMF induced on the coil. See here, you have a coil and EMF is induced on the coil which is static, which is constant, which is fixed. And when magnetic field is varying, see here, field is varying. What is the induced EMF now? It is transformer EMF. The EMF induced on the coil is transformer EMF. Whereas if we have kept field as constant, so now this field is static. I am just representing this bar magnet as a magnetic field, and now you vary this coil. Okay, now you vary this coil. You just try to vary this coil, push it inside such the way that like it will cover this magnetic field and bring it out. You just try to move this inside and out of this magnetic field. There will be again EMF induced. There will be an EMF induced, and this EMF is called as generator EMF, where the path is varying. See here, the path vary, but the field is constant. Field will not vary, or field is constant. Then also it will generate an EMF. You call it as generator EMF. Here it is transformer EMF. Any doubt?
No, sir.
Okay, good. Let me clear this now, and we shall go back to our friends Faraday's Lenz law. So what was the statement? The statement was EMF induced. EMF will be equal to minus d phi by dt. And why is this minus sign? Minus sign is due to the EMF direction to produce a current whose flux is against, right? Whose flux is against, so that it will reduce the flux in order to generate the EMF. That is what you mean by this minus sign. It will reduce the rate of change of flux with respect to time is reduced in order to generate the EMF. but EMF induced, or the voltage, this is also called as voltage. The EMF is a scalar quantity, and EMF is given by EMF is equal to E is equal to the line integral E into dl. And this will be the voltage with respect to a specified closed path. This is a voltage with respect to a closed path which is specified. So this is one part, but again coming back to this part, flux is equal to, flux can be written as surface integral B into ds, right? Flux can be written as B into ds. Therefore, what happens to the EMF equation? EMF will be equal to minus d by dt of surface integral B into ds. So I'll take this component inside, this differential component inside. So what happens? EMF is equal to surface integral. Okay, you can take minus also. Surface integral dou B by dou T into ds. It's a partial derivative. If you take this inside the integral, it becomes a partial derivative, and this is a surface integral. Okay. So this is a Faraday's law in integral form. And of course, you can equate this, these two equations also. You can equate these two equations also, right? Okay, like say EMF is equal to line integral E dl, which is equal to minus dV by dt of surface integral B into ds. And this is line integral, right? This is line integral. Okay, if I just try to extend the conversation here, you can join Divya Madam's class at 12 o'clock. No worries. I have already informed her. Just concentrate here. I'll just try to conclude this EMF equation due to Lenz's law. So which will lead to the Maxwell's, one of the Maxwell's four equations here. How to convert the line integral to a surface integral. So just take a curl of that element, right? So curl of that vector here. So this becomes what? Surface integral. So this is surface integral is equal to minus of surface integral of dou B by dou T into what? ds. So now if you try to equate the components here, so it would be curl of E is equal to minus dou B by dou T. So this is one of the most popular Maxwell's four equations. So this will be derived in future, but you need to remember the Lenz's law would stop here. So Lenz's law would stop here. Just an extension I did, I converted line integral to surface integral using Stokes theorem. Yeah, this is a Stokes theorem which introduces curl of a vector in surface, and equate the components, you'll get one of the Maxwell's. Okay, this is a differential form because you have dou B by dou T. And here this is an integral form of a Lenz's law or a Faraday's law. Okay, any doubt? So there are two conditions for EMF to get induced, as I told you already. There are two conditions. Make a note. Two conditions for induced EMF. For induced EMF, the first condition is changing field with a stationary path. Changing field, that is B is varying with a stationary path, and the path is stationary. And the other one is moving paths. Here now path was stationary, now the path started moving path in a constant field. In a constant field, you call this EMF induced as transformer EMF, and the EMF induced due to this principle, you call it as generator EMF. So there are two conditions for induced EMF. The first one, which we have already dealt with by deriving the Lenz law. So whatever we did to derive Lenz law is the induced EMF due to changing field with a stationary path, and it is called as transformer EMF. So again, we'll take up these issues one by one. The first, again you might get a a derivation for which satisfy both the conditions. So we know that if the path is stationary, and the field is varying, we call it as transformer EMF. Path is stationary but B varies with time. So you get EMF is equal to, since we already derived using Faraday's Lenz law, I'm just trying to use those equations here. Which is equal to minus surface integral dou B by dou T into ds. Is it okay? So this is what? A transformer EMF. Now consider these two equations. So the line integral EDL, I'll convert it into a surface integral using Stokes theorem. So it becomes del cross E ds is equal to minus surface integral dou B by dou T into ds. Therefore, del cross E is equal to minus dou B by dou T. And this is the differential form of one of Maxwell's four equations. So out of four, this is the one which we have derived in a differential form or in point form. You can also call it as in point form. Is this okay? So you have obtained this equation. I have considered this equation directly for the first case. Here, where I have not moved a path, the path was stationary, and I call it as transformer EMF. Now I will try to take the second instance here. Now I try to take the second instance. Now if the path is moving path with a constant magnetic field, with a constant field, and called as generator EMF. This is called as generator EMF. So now for this, let us consider a charge Q. Here, the charge Q is moving with some velocity. Let us consider charge Q is moving with some velocity in a magnetic field B. In a magnetic field B. So B is kept constant here. So B is constant. So what is the relationship between the force and the charge Q with velocity and this B? So it is given by F is equal to, using your Lorentz equation, if you remember, F is equal to Q V cross B. It's a vector product. It's a cross product. So you're trying to move a charge with a velocity V with a constant field. Why? Because I've made this B as constant, and move the charge. Why? Because these charges are on the surface of this path, isn't it? See, I've assumed a closed path here, and the charge is something, the quantity is related to this path, and this path is moving with some velocity V in a magnetic field here B, which is constant. This B is constant, and now you're just trying to move this charge quantity, which I have assumed it on the surface of this closed path. Here the path is moving. So path is moving. But what is F by Q? So I'll just try to take this here. So F by Q. What is F by Q? Is equal to V cross B. The remaining is V cross B. What is F by Q equal to? Can I call it as a motional electric field, EM? I'll call this as motional electric field, EM, which is equal to F by Q. Therefore, F by Q is equal to what? Electric field. F is equal to Q E. Therefore, F by Q is equal to E. Here, since this electric field is introduced due to motion of the path of the charge, so now I'll write it as EM is equal to V velocity cross B magnetic field. Now the EMF induced. I have the equation. I know the equation. EMF is equal to closed line integral E into dl. Now this is EM into dl, which is equal to closed line integral V cross B into dl. Now this EMF is called as motional EMF or a generator EMF. Motional or a generator EMF, and this is the equation V cross B dl. So here the flux will cut the charge point. This charge quantities, this charge quantities will be moving on this conductor due to the flux which cuts on this particular closed path while moving with respect to while moving inside out of this magnetic field, constant magnetic field. So now let me consolidate the equations. So the total EMF or the moving conductor in time varying fields, if the conductor is also moving, so if the path or a conductor is moving with varying field and subjected to. Guys, I am audible. Am I audible?
Yes, sir.
Yes, sir.
How about the screen?
No, sir.
How about the screen?
Yes, sir.
Okay, fine. So now I just want to conclude this. So if you have a field is also varying. Say you have a B is varying with respect to time, and the closed path which we have imagined, and this path is also varying. See, this path is also varying. So if path is also moving and the field is also moving, so in this situation, again the EMF will be induced on the closed path. See, this EMF will be induced, and that total EMF with respect to varying path, moving path and varying field. So that EMF will be equal to transformer EMF plus generator EMF, which can be given as EMF is equal to, so general EMF equation is E into dl, which is equal to, what is transformer EMF? Guys, what is transformer EMF which we have derived in the first case? Minus surface integral dou B by dou T into ds plus what is generator EMF, just now we have derived again. No, this is not a surface integral, sorry. This is not a surface integral. This is a closed line integral V cross B into dl. So this EMF is called as varying path and moving path and varying field. So this total EMF will be equal to transformer EMF plus generator EMF. So this is, if I call it as transformer EMF, and this is generator EMF. When this EMF is generated, the EMF is induced on the closed path due to the varying path. See, this is also varying. See here, this is varying like this. Even B is also varying. I cannot make these two things vary. So even B is also varying, and your path is also varying. So both are varying. So in general, so this and this both are varying. Hope you understood this concept. So in the next class, we shall discuss about displacement current or modified Ampere circuital law. Is it okay?